Welcome to this tutorial. My name is Wolfgang and I will introduce you to SimEvents using a classic simple example. Well, this classic example is a single waiting line system which can be applied to various other scenarios. Okay, what's the example? Well, we are going to look at a Seaport system. So if we look at a more precise challenge, well, there's lots to read. But all I want to say actually is, well, if you look at the formulas at the bottom, we can actually solve it analytically. So the solution for this one is given here. So we have got the length of queue, waiting time, and so on. So these are typical things which we would love to determine. So in particular, what we are going to look at is how many writers will stack up on average. That means we are going to collect some simulation statistics and we will figure out about 2.3 writers stack up. Then the second thing which we're interested in is how long do they have to wait actually. So again, we collect some measurements and figure out they have to wait on average 45.9 minutes. Alright, now let's start with it. That means, let's start with it. That means we need to start Matlab. Here we've got a typical Matlab window. And what we need now is a new Simulink model. So I'll start a new Simulink model, which should appear in a second. And we are going to rename that immediately once it has appeared. Okay. Having too many programs running in parallel. Probably have to cut this movie at the end to actually get rid of this long delay. It usually is significantly faster, but since I'm recording this video in the background, that really slows me down. Good. Here we've got an untitled Simulink window. So I'm going to rename, I'm going to save that now immediately as my Seaport, and save that. Okay, I've used it before, great. And Next, I will actually, well, I want to create my Seaport, so I need some components. So I'm going to open the library browser. So view library browser. And here we've got lots of libraries. What we are interested in is SimEvents. So let's have a look at SimEvents. Here you see we have got many possibilities, and first we would like to actually create the ships. So we need a generator, and we need to create the entity freighter. So, well, the freighters arrive on a random basis, so I need, well, what is the randomness? The time is the randomness, so I need a time-based entity generator. Good, so I just drag and dropped it into my Simulink window. I'll immediately call that source. And good, so the ships arrive, and sooner or later they are going to leave the harbor again, or they are docked and we are not interested in them anymore. So we need a sink to actually model that as well. So here we've got the sink. I'll rename that immediately to sink, so I have to have nice short names. And I'll connect that. And now my connection is black, so that means it's okay. And I'll immediately run this simulation. So here's the green button. I'll press the run. It's compiling. And I'll get some kind of message in the background. Let's see what it is. It says something like ordinary differential equations are used. Well, which we are not interested in all. So what we need to do is we need to switch to discrete event simulation. So here we are. We look at the model configuration parameters, and we are going to change, well, the steps, that's the solver, to discrete event simulation. As soon as it appears. Okay. Okay, let's just try it again. Maybe it's that's slow, maybe it's not. Okay, it actually works. But it looks much better. So here we are, and we are going to change the solver to discrete. Since we're already here, discrete event simulation, well, that allows us actually to jump immediately to the end, so we are changing the max step size to infinity as well, and apply that. So as far as we see now, the start time is 0 and the stop time is 10. Well, what? 10 seconds? 10 minutes? It depends on what you choose. So it's up to you to decide what it represents. Good. If we clear now the console quickly to see whether we get this warning message again when we run the simulation. Well, we don't get it anymore, so that's already good news. So the license is working and the solver is the correct one. So far so good. Well, actually we wanted to model the harbor master, so let's get rid of this connection and create the harbor master. So we are going to have we need our library again. Here's our library. Our harbor master is an operator which we call server. So here are the servers, and it's a single server. It's one person only. So let's put that in here and call, well, we could call it harbor master or server. Let's use the commonly used terminology in queuing systems. Well, where's the queue? Good question. So if the harbor master is busy, then the freighters have to wait. So that's the stacking up of the freighters. So where's our queue? Here are queues. So first in, first out. Queue is probably the most popular one, and we are going to use that as well. So let's connect all of that. Run the simulation again. We hear the dong, which means no errors, all connections are good. However, we don't see any results yet. This is a bit boring, I would almost say. Let's see, okay, what do we generate? So I'll double click on this on the source. Okay, I'll double click again on the source, and we want to collect some statistics, namely the number of entities which depart. That means these are the entities which we generated. Okay, now let's have a look at the sink and also collect some statistics. Say, okay, how many entities have actually arrived at the sink? Obviously, we're expecting that is roughly the number which came in. So if a writer comes in, then we have serviced it. Well, we want to display that, so we need to have a look, is there something where we can display it? Well, in the sinks we have a signal scope, so scopes are always used for displaying things, and I'll just, so I've got now one signal scope and I need one for the sink as well. So I'll just press the key Control and drag this scope block and connect it as well. So now when we run this simulation, okay, let's save it first and run, we should get and see what is actually happening in this system. Okay, so we had signal scope 1 and the other signal scope. So we do see, if we zoom in here a little bit, we do see at time 0 we have generated an entity, that means a freighter, and 1 second, minute, hour later we have generated the next freighter. So they arrive constantly. Every 1 hour arrives one freighter, for every minute. So now actually our data is comes into play. So that's not quite correct what we want, because we want 3 freighters to arrive per hour. So that means if we go to the scale of minutes, so every 20 minutes a freighter arrives, or every third of an hour. Okay, let's stay in the domain of minutes. So we will have to change that to, so the inter-arrival time, this is how we call that, is 20 minutes. And so as we see, we are using now a constant distribution still. Okay, so far so good. And our second objective is that the server is actually working faster. What we see here, differently. What we see here is it takes 1 minute for the harbor master to actually dock on the ship. So constantly, in a constant fashion again. Okay, so we are going to change that as well. And it takes him actually 15 minutes. So far so good. So everything is still constant. So right now we should see a couple of gaps if we run that again. Well, we see nothing at all. Well, why? Because we are running it only for 10 minutes and it takes already 20 minutes for a ship to arrive. So if we want to have about 10 ships, so we have to go to about 200 minutes. Okay, let's do that again. Now we see 200 minutes and we see our 10 ships. And what else do we see? Well, it takes 15, so every 20 minutes we have that, and after 200 minutes it's done. With the processing it's slightly different, but it all makes perfect sense. So next we want to actually insert the randomness into this process, and it would be actually nice to have this two signals overlaid to compare them better, to see better what's going on. Okay. To see better what's going on, we have to replace these scopes with other scope display, which is a commonly used block in Simulink. So we go to the commonly used blocks and use the scope. Again, same name, but it's a bit different. Unfortunately, we cannot connect both of them immediately. That's a bit of a shame, but however, there's a nice little tool which is called multiplexer, which we can use. So we use this multiplexer and insert these two signals, and these two signals combined into the scope. So now let's see what happens. Save and run. Can we compare it? Well, we do see them now occurring simultaneously. We do see, if we zoom in here, that it takes 15 minutes to service it. So what we have here, this area, is the system time. Well, what in the system time? System entities. Okay. So far so good. Well, we still would like to know what is the yellow color and which one is the red color, so we are going to change that. We are going to display the legends, and well, we need to rerun the simulation actually to display that. So now we have to actually close the scope every time we run the simulation, but we do get several benefits out of this. Okay, so far so good. We still have not integrated the randomness into this model. I'm going to do that right now. How do I do that? Well, again, instead of the constant distribution, I'm going to use an exponential distribution. And here we have a bit of a problem because we cannot select the exponential distribution directly. So, however, we can use the signal port to integrate our service time. So let's do that. So we need to get the signal in here. So we go back to our SimEvents library and look of how we could generate this signal. Here are signal generators, and we would like the event-based random number, which is actually our service time. So here we see now there are lots of distribution we can select, we can choose from. We are going to select the exponential distribution, And we said it takes the harbor master 15 minutes. We are going to apply that immediately and insert that into our system. So now when we run the simulation again, well, we get a warning message, which we should have seen already, that the random seeds are identical, which is not good. We could just randomize all links. Let's just click that link. Hooray, we have got 2 random seeds now. So what has changed here, if we look now into our model again, so if we look at the source, these random seeds are now represented in here. So they are different now. Before there were 1, 2, 3, 4, 5 identical, and we would like to have different random numbers to reduce the deterministic behavior. Okay, so far so good. So if we run that again, we should see now a more interesting graph, and indeed it looks now much more entertaining. Oh. Does it still make sense? Well, since it's exponentially distributed, we assume, oops, it doesn't make sense, because we need 20 minutes. And service time is still okay. Let's have a look again. Okay, this looks much more reasonable. What I wanted to say before was that when it is exponentially distributed, then we expect that the majority of, well, 1/4 actually in this case, of entities arrive immediately. Okay, so far so good. Now, where are we? Well, we actually wanted to answer a couple of questions. Let's remind ourselves, what did we want to answer actually? How many writers will stack up on average? So that's one question. Let's see whether we can solve that immediately. Stack up means they wait, they're in the queue. So let's rename that to queue. And our queue only has a capacity of 25, which is not quite true, because we actually have the whole ocean, so we can have infinitely many writers stacking up. And we want to actually know how many on average, so the average queue length. So far so good. So we need to display that as well. We have already seen that the scope is a very good thing to display things, so I'll just copy that. And this is our queue length. Queue length, the average one. Good. Let's save that and run. And what do we see? Well, we don't see much. We see a big fluctuation, which stabilizes a little bit, but not really great. So now an interesting question is, how long should we run that actually? So we are in the scale of minutes. So we have got 60 minutes in an hour. In a day we have got times 24, and in a year times 365. So maybe that's a reasonable number. So this should be a reasonable number. So in general, we are interested in the utilization over a long period in a stable condition. 200 minutes, that's just 3 hours. We can't really make a conclusion out of 3 hours. The randomness is far too great. So what do we see here now? We do see now, well, first of all, our time scale is not the complete one. We are only displaying the last bit of the simulation, and we are ending up with something around 2.4. Well, we said 2.3 actually initially, and if you picked it up during the presentation, the theoretical one, so if we look at the theoretical one, is actually 2.25. So it's not quite right, and this is why we usually do replications in a simulation in order to see what happens if I change the random seed. So if I change the random seed here to 1, 2, 3, 4, 5, then I should get something slightly different. Let's see what we got. Well, now we got 2.17. So on average, we are actually approaching it. So that's good news. Can we actually see it display the whole queue length, how it varies? Yes, we can do that as well. So if we go here and record the history, the complete history, so that means we don't limit the data points, and apply that, and rerun the simulation, then what we have noticed now is we are recording it from 0. We also notice that there is a transient phase before it starts stabilizing. Okay, so far so good. Well, this is one answer, so we are already in the right region. This is good news. Is this error acceptable? Yes, in simulations it's acceptable. 5–10% error is actually not too bad. Can we improve it? Yes, we can by doing several replications with different random seeds. We could increase the duration, but since the random number generator is actually starting to repeat itself, it doesn't really have too much of an impact. So replications are much better. Okay, the second question which we wanted to answer was, if we go back here, how long do they have to wait on average? So let's go back to our statistics and say what is the average waiting time. Okay, so we need another scope. Waiting time, average. So here we are with the average waiting time. Let's save that and run it again and see whether we have got the 45 minutes. Well, that doesn't look too bad. Let's zoom in. Yes, it's pretty close to 45 minutes. So we are very happy with that. So we saw two important operational characteristics: the waiting time and the queue length. So of course we would be interested as well in what is happening in the server, in the operator, but we do know that actually already. We know that the service time is 15 minutes. on average. So we do know already that the waiting time of 45 minutes plus the service time of 15 minutes is 1 hour. So we do know all time characteristics of the system. We do know that the queue length is 2.25 on average. The utilization of the service, do we have an idea about that as well? Well, we do know it takes 15 minutes to service one freighter, and every 20 minutes one arrives. So we do know the harbor master should be on average 5 minutes idle, and the other 15 minutes he works. So the utilization of the harbor master is 75%. Okay. So what does that mean actually? That means that on average 3/4 of a freighter is under service. So that means the number of freighters with the operator is 3/4, which means the total number in the system is of course the 2.25 plus the 3/4. That means 3 freighters are on average in the system. So these are all our system characteristics. Alright, so far so good. Now, what else could we do? What else could we see? Can we see perhaps more of a service level point of view to actually say, okay, 45 minutes they wait on average, but I have no clue on how many ships are this. So, well, can we do that? Well, if we look at the statistics, we don't really see that. We cannot really see the individual waiting time of each entity. However, we are now actually in the position, we can create something that records all these entities, all the times of the entities. So how do we do that? Very easy. We go back to our library, to our SimEvents library, and well, we would like to observe the timing. So we know when did we generate it. Okay, this is when we start the timer. So I'm going to resize it a little bit. So this is when we start our timer. So entity is generated, we put it into the start timer. That means a time tag is attached to each entity. Now, well, we have to stop the timer somewhere as well. So read this timer. This is done well after the queue, because we want to know the individual waiting times. Why do we want to know the individual waiting times? To determine the service level and know how many of the freighters have waited for which time. Good. So we read the timer, so we want to do something with that. So what do we want to know? Well, we want to know the elapsed time. So good, so far so good. So all we need now is a scope. And this is not anymore the average waiting time, this is the waiting time per entity. Let's save that and run it again. Now, what we see is, well, a yellow bulk. Let's zoom into that a little bit more. So we see something like a random noise. We would have expected an average waiting time of 45 minutes. It seems to always overshoot that. So if we zoom in a little bit more to investigate on that, we see already a couple of faults. Let's zoom in again. And we do see now that there are quite a couple of faults which might indicate that this graph is actually correct. Well, let's not trust it too much yet, but let's rather see whether this is really correct. Well, we can't see very much with this scope, so we have to go to export it to Matlab actually. We can do that very easily by just just saying that we want to export it to Matlab. So here we are again, and we saw the history already, we did not limit it anymore, and here is another option which actually allows us to save the data to the workspace. And we are just going to call it W for waiting time. And its structure is nice, but we prefer an array because we can see immediately things with it, and it's just the waiting time actually which we are interested in. So there's not too much into it. Of course, we get a second axis as well, the x-axis, which is the time when we recorded that, which we're not interested in at all, but so we can just delete that. Let's okay, let's run the simulation again. And now we see our waiting time array has been created. We do see it has 2 dimensions. Okay, let's have a quick look at it. 2 dimensions, and this is when it was recorded, and this is actually the waiting time. So 4 minutes, 9 minutes, 14 minutes, and we do see a lot of them have actually not waited. A lot of writers had not to wait at all. So we're not interested in this one, so let's just delete that. Delete column and close the workspace. So we see now it's only 1 dimension now. Now we can plot it immediately, that's the nice one. We see exactly the same as before, that's good news. And now let's display it as a histogram. That's a very rough histogram, as we see here. And as we see, the 0 values are really dominant. Anyway, let's display this histogram again with another option. Let's have more bins. Let's have 200 bins. We actually don't need the get current figure. So now we explicitly see all the 0 values here. Well, so most ships don't have to wait. And what about the ones which have to wait actually? Well, if we only want to have them which have a waiting time which is greater than 0, then we have to identify them. So waiting time greater 0, waiting time greater 0, and now we do see they seem to be exponentially distributed, so quite interesting. Can we see more? Can we see actually the average? Well, of course we can just compute the average, which is 43.7 minutes. Agrees with our 45 minutes very well. Now let's go on and have a look at more statistics. So we just plot that again, because with this plot we can go at tools and have data statistics. Here again 43 minutes. Then we do know now the median, which is 22.76 minutes, so 50% of all the ships don't wait longer than 22 minutes. Okay, let's have now a look and say, how about 90% of the ships? There's a function which is called percentile, if I'm not mistaken. Well, there's definitely one. Percentile. Okay, here we go. Of the waiting times, and let's say 90% of the ships don't wait longer than 2 hours. Here we go. So that basically shows us all the statistics which we would like to have, so we can display them in a nice neat histogram.